Hey, it's part number 2 of the Audiopipe modification video. In part 1, which if you haven't seen, you have to watch because otherwise none of this will make any sense, we compared an Audiopipe which was a copy, direct clone of a Tyrant's HD3000, and we tried to figure out why it didn't make its rated power, whereas the amp that it's copied from, the HD3000, does kind of make its rated power. We wanted to look at what they did wrong. Why was the copy so bad that it struggled to make its rated power when the amp that it was copying from did? And once that had been figured out, the idea was to modify the Audiopipe amplifier to not only make its rated power that the amp that it was copied from is designed to, but also go above and beyond and try and make as much power as possible from this tiny little board with some clever modifications, tweaks and adjustments to the circuit. So go and watch part 1 if you haven't already, but for now, let's crack on with the modifications, and this is gonna get interesting. So, in our previous video, we decided to wind up a new, larger transformer using a lit wire, but so that I don't end up ordering way too much or too little, I'm going to temporarily wind it up using some single solid core wire to work out the rough lengths I need. I'm winding it up to the same specs as the original Tyrants to start with, 2 turns on each primary and 14 turns on the secondary, to make sure that the core is going to be happy here. For testing purposes, it's going to be easier to run some leads to the transformer off to the side of the board to prevent damaging the pads and make ongoing changes easier. With our new transformer core temporarily wound up, on powering it we can see the power supply drain waves here. It's a little bit ringy at the turn-on point, likely due to the quick, less than ideal test wind or extra cable hanging over the board here inducing noise, but working beautifully with the 14 secondary turns, giving us a near-on identical rail voltage to the Tyrants, with the output switching looking perfect and the amp drawing very little idle current. Great! First test complete, but now we need to crank this thing up and start preparing for a lot more rail voltage. The stock factory rail capacitor, rectifiers and output feds are good for 200 volts and the little film filter caps are rated at 250. That's quite a bit of headroom, so for our next quick test we're going to see how the stock board copes with around 180 volts of rail. I don't want to go too close to the 200 volt mark as spikes and ringing can bring it briefly over the limit of these stock parts. To do this, I'm going to add a few more turns onto the secondary and power the board up with a low input voltage first around 9.8 volts and gradually increase it until we see the desired rail of about 180 volts. So our first attempt at powering this up with the higher rail voltage made me realise that I need to address the over voltage protection circuit, since on this amp the reference for the PIC is not only taken from the battery terminals but also from the rail voltage level itself. So without making any changes to this, when we try and push the rails up, it'll just go into protection mode. 2 flashes of the protect LED signifies over voltage on the Audiopipe. So yeah, let's try and figure out how this works and how we can modify it. The rail voltage itself should be fed through a few high value resistors and then into one of the PIC input pins for it to read. And after a few minutes of poking around, I discovered exactly that. Over on the left hand side of the board, rail voltage is connected here. Then firstly goes through a 4700 ohm resistor, then through a 10k and then finally an 18k. So it's stepping the rail voltage down to a low safe voltage for the PIC to read. While I was looking at this, something hit me. If the Audiopipe is a direct copy of the Tyrants with all the same resistor values everywhere, just accidentally too low a rail voltage, then that would cause the Audiopipe to technically go into low voltage protection way too early, way earlier than it should do based on the Tyrants, but it doesn't. So I took a close look at these resistor values between the Audiopipe and the Tyrants, and I found that they're actually different. So the Audiopipe's resistors are calibrated for its lower rail voltage. This is quite the turn of events. This suggests that the lower rail voltage of the Audiopipe was actually intentional. Maybe they've done this as an attempt to improve the reliability of this circuit design, or maybe it was still a mistake, but they found that for some reason the amplifier was going into protect too early and they figured out which resistors were responsible for that and changed them, still unaware of their accidentally 2 less turns on the transformer. But let's say for a minute that this was actually intentional and they did change a bunch of resistor values on here to account for the lower rail voltage. They still rated this board as a 3000 watt RMS amplifier, knowing full well that actually it's not going to make the 3000 watts anymore because the rail voltage is too low. And again, if the lower rail voltage was deliberate, then why did they still use 200 volt parts like FETs and stuff? They could have used some 150 volt parts, which would have yielded better capacitors and higher current, lower RDS MOSFETs. Anyway, let's just power up the TARAMPS board and take a look at what voltage we have on the rail voltage sense pin of the PIC after the resistors, and that will give us a reference voltage to shoot for when we start calibrating the protection circuit on the Audiopipe after we've done our mods. After the resistors dropping the voltage down, we have about 2.2 volts. But with this information, let's try and get the Audiopipe powered up. And to do this, I'm going to take a little 10k potentiometer and wire it in series between the rail and the first 4700 ohm resistor. This will allow me to further increase the overall resistance and drop the sense voltage to the PIC down to its safe window that the PIC will allow operation in. Let's add a little more resistance to start with and bring the resistance of the pot and 4700 combined to just over 7k. Now the amp should power up and stay operational with a much higher rail voltage. And indeed it does. The amp seems to run perfectly happy up at the not much higher rail voltage with only 9.8 volts of input. However, while increasing the input voltage from the 9.8 up to see what happened, I noticed something curious was happening with the switching PWM on the output FETs. It appears that the duty cycle is dropping with an increase of rail voltage. I don't think I've ever seen this happen before, or if I haven't noticed it. Let's investigate. In almost all other Class D amplifiers I have seen, Class D PWM is fixed at 50% duty cycle. This will allow for equal clipping of the sine wave at the top and the bottom, since if the audio modulates the duty cycle around anything other than a 50% resting point, it ends up being closer to touching one extreme than the other, therefore it'll clip unevenly. Since this amplifier only uses a single positive rail voltage, the level of duty cycle directly affects the floating midpoint, which the sine wave uses to swing down to ground and up to rail from. You can see this DC midpoint present on both speaker terminals at all times with these amplifiers. When the duty cycle is at 50%, the midpoint is exactly halfway between ground and rail. If the duty cycle decreases as the rail increases, the midpoint ends up being closer to ground, so of course our sine wave will clip there first. The same happens if we go over 50% duty cycle, the sine wave will then clip at the top first. It's unclear to me why TARAMPS have designed it to behave this way. At first I thought it was to do with the rail sag or droop when the amplifier is loaded. So when you draw current across the output section, it'll cause the rail voltage to sag down or droop, which I explained in part 1 of this video. I thought that perhaps the lower midpoint between the rail and ground would compensate for when the rail sags down. It would then allow the sine wave to clip equally again because the rail top is now sagged down, so it's about halfway again. But then I was like, no, if the rail is sagging down, then because it's getting lower, the duty cycle will compensate and change for that. So now the midpoint will be different again. It will now clip at the top too soon, which actually is shown in part 1 of the video. You can see the top of the sine wave does clip before the bottom. So a more likely reason that this has been done is to limit the total amount of clean power that this amplifier can produce when the rail voltage is much higher. So this is rated for 3000 watts RMS at 12.6 volts. Now on paper, based on square law correction factor, when we increase the input voltage from 12.6 to 14.8, the amplifier should try and produce about 4140 watts RMS, which might be just a little bit too much for the stock components on this board to produce reliably. So by reducing the duty cycle and causing the output sine wave to clip early when the rail voltage is higher, you're essentially causing them to clip early and therefore produce less total output power with a high rail voltage versus what it's rated for at 12.6. Either way, we need to figure out which components are responsible for this behavior and modify it. Because if we don't, then our plan of shoving a high as hell rail voltage up its ass is going to be a complete waste of time, since by the time we reach a nice spicy rail voltage, the duty cycle will be like non-existent and the amp won't do much more power than it did to start with. This part took me a little while to figure out. I started by consulting the datasheet for the IRS-2092 drive IC, which is responsible for running the outputs, looking for some kind of obvious duty cycle control pin, but there was nothing. Dead time is something different, which I won't cover here. It didn't help that the example circuit in the datasheet was based on a normal dual rail amp design either. So I started probing various points on the output drive circuit while the amp was powered up and varying the voltage level so the duty cycle changed, and I looked for some kind of changing voltage that moved with the change in duty. Nope, no luck here. Everything stayed the same, regardless of the rail voltage level. I considered whether the PIC might be responsible, it might be programmed to change the duty with a rail voltage level, so I varied both the rail sense and battery voltage sense pins with a potentiometer, which made no difference to the duty cycle either, so it wasn't the PIC. I was starting to clutch at straws a bit after spending many hours staring at this circuit, pulling random resistors and parts to see how it affected the operation. But then, I had an idea. Taramps make a 2 ohm version of the HD3000. This is the exact same board with a higher rail voltage and a few different components to work with. Kind of the same as what we're doing with this mod. So this is my key then. The 2 ohm version naturally is going to have a much higher rail voltage than the 1 ohm version, which means that there should be some different value components or resistors on the board somewhere in the 2 ohm version, which will allow a more normal duty cycle at the higher rail voltage that the 2 ohm version uses. So by comparing the component values between the 1 ohm and 2 ohm, I'll be able to find my answer. So I spoke to a few friends and managed to gather a list of the differences in components between these two versions. I deeply believed at this point that my answer must be in the feedback circuit somewhere, so there were 4 resistor values that caught my eye which differed between models and sat between the output switch wave itself, the input pin of the 2092 and ground. I decided to experiment with the resistor to ground first, as changing the amount which it pulls on the surrounding circuit is likely to be what I'm looking for. When inspecting these resistors on the Taramps versus the Audiopipe, I was shocked to see that they are actually different. This strengthens the idea that actually the Audiopipe was deliberately sandbagged and component values were changed throughout the board to compensate for the lower rail voltage present, I guess in an attempt to make them more reliable. So I removed these 2 resistors and I connected one side of the pads through a potentiometer to ground, allowing me to vary the resistance while the amp was powered up to see if it affected the duty cycle. And lo and behold, yes! We have full control of the output duty cycle and therefore the floating midpoint which the sine wave oscillates between. It was a fantastic feeling to find this and to see the duty changing with my input after so many hours of wondering what's going on. So good. This will allow us to calibrate a perfect resistor value to replace these with once we've decided on our final rail voltage. At the moment, the rail voltage level will still affect the duty cycle once we have completed our mods. It would be better to somehow fix this to a 50% at all times, giving us equal clipping, since we aren't bothered about limiting the power anymore at different rail voltage levels. But for now, let's leave it at that and move on with the mod. So now that we've got this board to the point where it's happy powering up and staying running with a much higher rail voltage, we need to decide how high do we go with this. Naturally, the more rail voltage we pass through the board, the more potential power this can make. But also with more power comes a much higher current across all the components on the board. Now, in most cases, when you're building an amp and you're putting more power into it, you just add more parallel components so that they share the load better. But we need to fit this into the original heatsink still. So we are limited with what parts we can put in here, and we need to make sure that they can handle the amount of current that's going to be passing through them with the amount of power we're asking from the amplifier. As the voltage limit of electronics components increases, generally you'll find that the current handling of them dramatically decreases. This means that if we start going too high on the rail voltage, it might become hard to find parts that are high enough current rating to survive with the amount of power the amp will be demanding from them. Normally, you would just add bigger numbers of the lower current, high voltage parts in parallel, but in this instance, we have nowhere to put them. So we're going to have to stick with only 4 FETs in the output section, meaning they need to be as high current and low resistance as possible. There is just about enough space for us to fit larger packaged parts though, stepping up from the original TO220s to some TO247AC or even bigger variants of that. These typically have a larger die size and therefore can dissipate more energy away to the heatsink. The Banda transformer we stole here is used in up to the Viking 8000 series, which can produce over 10,000 watts RMS and uses a total of 8 200 volt output FETs. If we start pushing our rail voltage much above what's originally used in the Banda, we could risk saturating it. We also have much less space for FETs and a smaller heatsink here, so I think it's going to be sensible to look at some really high power FETs in the 250 to 300 volt range, as even if we don't push the rails up that high, having a headroom on the voltage limit on the FETs is a good idea when you're switching them. So with all that in mind, let's start whacking in some new parts. The first ones to replace are the power supply FETs. I popped the board back in the heatsink and checked to see if I could fit the larger TO247AC package FETs in here instead of the stock 220s. It's a tight squeeze, but yeah, we can just about fit 8 larger FETs along the heatsink here. I decided to go for IRFP 7430 PBF. As you can see, extremely high current, power dissipation and a nice low RDS. In order to attach them to the board, we need some precision leg bending action to line up with the original holes, and since the legs are slightly thicker, the holes needed to be drilled out ever so slightly bigger. Drilling the holes like this will actually get rid of the via, which transfers the current from the top board to the bottom, so it's important to physically solder from both sides to ensure a good connection. The original lead-free solder on the back of this board looks absolutely jank, doesn't it? The tar amps is a much nicer finish. The next parts to go were the rectifiers. These amps originally used one common cathode and one common anode rectifier. We could fit some TO247AC parts here, but finding common anode parts is almost impossible these days. The next best solution, and possibly a more reliable one actually, was to use 4 powerful TO220 package single diodes and connect them up manually in a common cathode and common anode arrangement. The parts I went with were the MUR1540G, which when linked together will equate to a 30 amp 400 volt common rectifier. You can see here in the tester, by joining the right legs together, we can create the part that we need for this circuit. Visually, it's not as clean looking, but electrically this is sound, and we have a lot more metal on the heatsink with these. A little bit more leg bending action and it's ready to be mounted into the original positions, leaving just enough space for some larger output MOSFETs alongside. Now we need to put some higher voltage rail caps in. I went for some 250 volt caps and got a range of different sizes to squeeze in and around the board once the rest of the mods are complete. For now, we only need to fit one in the original location to continue powering the board up safely. With these parts fitted so far, I did a quick power up to make sure that it was happy and working well. Power supply FETs were switching good, with the stock value gate resistors being low enough and the rectifiers were working as intended. Now for the most important part, the output FETs. Like with the power supply, I can fit these larger TO247 Max parts in place of the TO220s, with some precision leg bending again and drilling. After a lot of research, I ended up going with IXFX150N30P3, it's a bit of a mouthful, which are some absolutely monstrous 300 volt FETs, yet they're surprisingly easy to drive and fast given their ridiculous power handling. For the very first power up with the new output FETs, I removed a bunch of wires from the secondary of the transformer to keep the rail voltage nice and low and safe, just in case I had missed something and I didn't want to kill these pretty expensive output FETs just yet. On the first power up, I noticed it struggled a bit to start oscillation, with each pulse attempt actually causing a flyback effect on the output inductor, raising the rail voltage up quite considerably. Look, it's kind of bumping up, before finally latching into oscillation and dragging the rail back down to where it should be. I need to watch out for this. We don't want that happening when we have our final high rail voltage in place. I believe part of what caused this was the much lower rail voltage of around 46 volts I was using here, which prevented good feedback to the chip for self-oscillation. And the reason I think that is because when the flyback effect boosted the rail voltage high enough to about 60 volt mark, the oscillation kicked in just fine. We have a reasonably low idle current of around 1.9 amps, and here I'm probing the gate and drain and I'm checking for switching losses on the output FETs. There's a little bit of an overlap here, but it's very similar to what's actually present on the stock HD3000, with both of these new FETs and the original factory output FETs heating up to around 38 degrees Celsius at idle when they're not clamped to the heatsink, so pretty similar operation to the originals. The dead time is already fixed at its lowest setting on these 2092 chips, so there's nothing I can do to improve the switching losses just yet, but it's acceptable anyway. I did notice that there's quite a shock on the gate waveform when the FET switches on, just at this point here, which isn't present on the stock HD3000. That's probably due to input capacitance or the gate charge of these bigger FETs. We may be able to clean it up, but for now it doesn't really seem to be causing any ill effect. Okay, now the slightly scarier part. We're increasing the rail voltage and hopefully it stays together. Firstly, I'm going to bring it back up to about 100 volts of rail, and it does actually all seem to be behaving quite nicely here. A quick check of the FET temperature, around 47 degrees Celsius, not wildly high. It would be nicer if they run cooler, but we might be able to look at that later. Also, notice how now I have a load connected at the speaker terminals. I noticed that this helps the oscillation initially start up greatly. See how much easier this started? Look, turning on and instantly we get oscillation, and this is now at the 120 volt rail mark. So I kept on increasing the rail voltage of this, adding a few more turns, checking it, adding a few more turns, checking it, to see how it behaved with all the new parts and with a much higher rail voltage. I was kind of aiming for up to around about the 200 volt mark because I wanted to stay within the boundaries of the 250 volt capacitor I fitted. I didn't want to really go stupidly high on the power that this thing we're asking it to make, but as I approached, the sort of 150, 160, getting towards the 200 volt mark, I did run into a couple of issues when the amplifier starts output oscillation. When the amplifier tries to start building the Class D switching on the output section, there seems to be a bit of a spike sometimes, and I did have a load connected at all times, but sometimes when it would try and power up and start oscillation, it would kill the IRS 2092 drive chips, and a couple of times it killed the 15 volt Zenas as well. Now I believe that a couple of reasons for that are either to do with the fact that I had imbalanced resistors on the feedback circuit. So remember how we had this potentiometer and I had the potentiometer changing the value of one of these resistors, but I noticed that on the stock board and in all the documentations there's two resistors that should be equal value that probably form some part of voltage divider. So I had an imbalance there where with a much higher rail voltage I was naturally changing the resistance of that to keep a 50% duty cycle to quite wildly different to what it was intended to be, and I think that the two resistors there to form that part of that voltage divider or whatever it's doing need to be the same value, which might have been causing my turn on problems. Additionally, I might be running into issues where even though we've only got 4 FETs on the output section and we've got one chip per bank, so we've only got one MOSFET on each of the outputs of the drive IC, perhaps they're just a little bit too hard to drive, or we need to make some changes to the actual drive, the gate resistor or part of the diodes in the output section, so that the MOSFETs aren't quite as hard on the chip when turning on. We need to make some changes there, potentially to the feedback circuit or the final sort of drive circuit there. But it's all minor stuff. Like, I did get this up and running and playing some audio with pretty high rail voltages. It was just a little unreliable to turn on and off. So that is some things that I'm going to be tweaking next. So going forward, in order to do that, I want to discard all of that temporary winds on the transformer, and I want to wind the transformer up with the final high quality wire that we're going to be using. And I worked out roughly the amount of turns that I need for around about the 200 volt rail limit, and it will change with 12 volts or 14 volts, but around about the 200 volt mark I worked out the rough length of wire that I need. Now, I was going to use Litz wire. Remember from the first video? Anthony recommended we use Litz wire for a bunch of reasons, and I can change the switching frequency of the power supply FETs and to make it, super high power density. But man, finding Litz wire in the UK at least is freaking impossible. You've either got to buy it in like 10 or 50, 100 kilogram bulk orders, or it's just very complicated to how you got to buy it. Like, I just need like 7 meters of a specific size Litz wire, and it's proving bloody impossible to just get that. I'm either going to have to buy too much of it or super thin stuff like that I'm going to have to buy a shitload of, and it's going to end up costing hundreds of pounds. So I'm going to look into it a bit more, but I think we might end up just having to buy some like thin strand, you know, insulated, laminated wire, some really thin stuff, and just parallel loads of them together to give us a kind of Litz wire, but not quite as thin strands, not quite as good as Litz wire, but it should still be absolutely fine for the purposes of this, with the kind of frequencies that we're going to be running through the power supply. So, you know, at the end of the day, we're going to be kind of limited to whatever frequency these MOSFETs can switch at anyway. Like, these are some pretty beefy MOSFETs and they're quite slow to turn on and off. So I imagine we're probably going to end up hitting the speed limit of the MOSFETs before we really reach the speed limit of the transformer anyway. So maybe using Litz wire was a bit overkill in the first place, but that's the plan, is to order some wire, get the transformer high quality wound, you know, really nice and tight, equal space windings, so that there is minimal ringing, and just so that that whole thing is done and perfect, so I know that any issues with the amplifier aren't coming from the way that the transformer's wound. So get that done first. Then I ordered a bunch of different surface mount resistor values for the feedback circuit to get the dead time married up to exactly where I want it. So literally I ordered so many different values so that I can make them equal, make them the same. I didn't want to wire up another potentiometer, because the potentiometers are slightly, you know, the tolerances are slightly out with them. It's very, very precise movements. I wanted to just drop in some fixed resistors and use that to power the amplifier up with a higher rail to kind of get the dead time that I want, and make sure that my issues with killing the 2092s weren't down to, you know, the potentiometer setup. That was basically just as a proof of concept to make sure that I could vary the duty cycle with rail voltage. And now I figured that I could, we need to get rid of that potentiometer and put some fixed value resistors in there. So that's the next thing that we're going to do as well, and make sure that it is happier powering up and more stable going forward. And lastly, because we are putting quite a considerable amount more rail voltage into this, not only is obviously the rail to rail switching going to be much higher voltage than I originally anticipated or this amp was originally designed for, but also the amplifier is going to be doing quite a lot of power. So I have decided, even though I said I wasn't going to in the original video, to modify the output inductor. So this is the original output inductor. You can see the small core there. I've actually taken one of the winds off it already. I think I'm going to be using, I might end up using actually the original core from the transformer of this amplifier, use that as the output inductor. In fact, see, pretty beefy, chunky, fits on there. I can probably get it to fit in there in the original location. I actually do have quite a few spare cores laying around, all bits and pieces, so I'm going to be checking the inductance of the core, find out the material, and then I'm probably going to end up winding up the new inductor with a higher inductance, a bit more dampening, you know, which should help with the output section cleanly build self-oscillation. It will take some stress off of these film capacitors in the filter network as well, and being a bigger core, I can put some thicker wire around it and stuff like that to make sure that it can pass the additional power we're going to be asking from this amplifier now. There's a lot of other stuff we need to do to the board as well to make it happy with the additional power, but I'm not going to go through that now. You have to wait till part 3 for that. So guys, that is part 2. I really wanted this to just be one video, you know, just the mod, and I wanted this to just be one thing where start to finish we end up with the mod completed. Turned out to be a lot more complicated than I had anticipated, and a lot more footage than I had anticipated, so I didn't want it to be like a 2-hour long video. I wanted to split it up into small bite-sized chunks that you can easily digest and follow along, and also because it has turned out to be quite complicated, there's quite a lot of research in between the videos and stuff that I need to do, a lot of testing, and I didn't want it to just be like super long time before I get this content out. So this is a part 2. This is the progress so far. Part 3 will be the amplifier up and running, back in the heatsink, and I will be performing some power tests on it. I'm not going to tell you guys how much power the amplifier makes myself. What the plan is once these mods are all finalized and I am happy that they are reliable and I've run my own tests, I will be doing some videos of this amplifier in the van. I'm going to hook it up to the Vito with a DD Z415s. You've seen them in the Digital Designs M4000 video, and we're going to see how loud it is, do some hair tricks hopefully from this tiny ass amplifier, but I won't be telling you how much power it's making. Are we going to wait for it to go back to Dereck before you guys see how much power this makes. That's going to be your incentive to watch Dereck's dyno video once it goes back over there and see how much power it's really making. But part 3 will be coming as soon as possible. I'm working super hard on this mod, and it is much more complicated than I had anticipated, so it's taking a bit long. I do apologize, but I wanted to get this next segment out for you so you can see some of the process I went through in the modification so far, and get you excited about how much freaking power this is going to make and how it's going to sound in the Vito. I am so excited to hook this up to the Vito. It's going to be freaking hilarious. It's going to be this tiny little amplifier. It's just going to be that on the back of my wall in the Vito, and hopefully like hair tricking and flexing the crap out of it. It's going to be freaking jokes. So definitely subscribe, stay tuned, because part 3 will be something hilarious like that, with the modifications done and the amplifier working stable. And then once I have tested it enough and I'm happy that it is stable, I'll be sending it back to Dereck, and you can check out how much power it now makes after the mods on the dyno. So guys, it's been a pleasure. See you next time.